So, welcome to lesson 2. In lesson 1, we introduce you to integral equations. So, in lesson 2, we'll be talking about classification of integral equations. Now, we're going to classify integral equations, okay? So, we are going to do the following classifications. So, we are going to classify integral equations based on linearity, and based on that, we'll have linear and nonlinear integral equations. We are going to do that based on the kind. So we have first kind and second kind based on homogeneity, and based on that we have homogeneous and non-homogeneous or inhomogeneous. Then the type. So based on that we have the Fredholms and the Volterras. Then we have other forms of classification. So we'll introduce you to what an integral differential equation is. Okay. So let's start. So linearity. The linearity of an integral equation is defined with respect to the unknown function y of x. So from our previous video, you should know what the unknown function y of x is. So that is if it is of the power 1, right? So, however, nonlinear integral equations arises if y of x is replaced by a nonlinear function. So I hope you get the definition, okay? So let's take an example. So we are saying these two are examples of linear integral equations, okay? And the reason why it is so is that you know the unknown function is only appearing here, right? And you can see that it is of the power 1, right? So there's what makes this linear. Then when you take the second one, the unknown functions appears under the integral sign and here as well, okay? So here this tan x is the free term or the forcing term. So you can see that here y of x is of the power 1, here too y of t is of the power 1. So that is why this one is also linear. Now let's take examples of nonlinear integral equations. So you can see that here we have y of t of the power 1, but our y of x here is squared, okay? So this power 2 here, that's what makes this nonlinear. Here too, we have y of x here and we have squared here. So this squared here is what makes this integral equation nonlinear. And here, we have our y of x here. When you come here, you could see that this thing here is replaced with what? Transcendental function, right? Making it nonlinear. That's the e y of t, okay? So that's the reason why the third example is also non-linear. Alright. I hope you understand the classification based on linearity. So now let's go to the classification based on first kind and second kind. So an integral equation is said to be of the first kind if the unknown function only occurs under the integral sign. So if the unknown function y of x only occurs under the integral sign and nowhere else. So otherwise, if it occurs both under the integral sign and elsewhere, then it is of the second kind. Okay, so for instance, you see with this, for instance, the unknown function only appeared under the integral sign. So that means if we were to classify this based on kind, this would be first kind. However, here, the unknown function appeared under the integral sign and elsewhere. That's this place. So you can see it is here, it's also here. So this will make it the second kind. Okay, let's take more examples. So, example, this is the first kind because our unknown function only occurs here. That's under the integral sign. And this second example is the second kind because our unknown function appears here and here. Do you get it? So under the integral sign and elsewhere, okay? You see it's quite simple. Okay. So now let's classify it based on homogeneity. So whether it is homogeneous or non-homogeneous. So you know what a free term is, or what a Faltine term, f of x. So if the free term or the Faltine term of x is equal to 0, then we have a homogeneous equation. And that equation always has the trivial solution, y of x equals 0. So the key thing you have to know is that is the free term, if the free term is 0, then our integral equation is homogeneous. So otherwise, the equation is non-homogeneous. So an example is this equation here. You can see that we don't have any f of x attached to it. If you compare it to the general form of an integral equation, the general form is y of x is lambda integral from a to b k of x d y of t dt plus f of x. But you can see here we don't have any f of x. Alright, so since our f of x is 0, then this is homogeneous because our f of x is 0. But here you can see that our f of x is what? X. It's not 0. So we're going to have a non-homogeneous integral equation here. What we can see is very simple. So now let's go to classification based on type. That's whether it is a Fredholm integral equation or it's a Volterra's integral equation. So this one is also very simple, okay? So with the Fredholm's integral equation, this once the limits b and a are constant, so they are constants, okay? Then the integral equation is called a Fredholm integral equation. We have two equations here, and they are the Fredholm's equations of the first kind and the second kind, okay? So you know first kind because here our unknown function is still only appearing under the integral sign, but this is second kind because our unknown function is here, it's also here. Okay, so this is a Fredholm's integral equation because the limits of integration AB are constants, okay? So they can take 0, 1, 2, 3, they are constants. So the Volterra's integral equation. So if in the Fredholm's integral equation, the constant b is changed to a variable x, then we have a corresponding Volterra's integral equation. So you could see that this is the same as the first kind Fredholm's integral equation, except that we replace the b with what? The variable x. In the second kind, to replace it with what? X. So when the b in the Fredholm's is replaced with a variable x, then now we have a Volterra's integral equation, okay? So there's the first kind, there's the second kind. I hope you understand. So now let's go to integral differential equations. So these are equations in which an unknown function y of x occurs in one side as an ordinary derivative and appears on the other side under the integral sign. I think the definition is quite simple for you to understand. So you can see here our unknown function is under a derivative, and here too the other side is under the integral sign. So this makes this equation an integral differential equation. Okay, so let's take some exercise based on what we've done to help you understand things better. So you can pause the video and solve the questions. After that, you compare it to what we have. Okay, so the question is, classify each of the following integral equations as Fredholm's or Volterra's. linear or nonlinear, homogeneous or non-homogeneous, and first kind or second kind. Okay, so we have these three integral equations. So you can pause the video and try to solve them and see. Okay, so let's take the solution. So with the first one, it is Fredholm's because the limits of integration are what 0, 1, and they are all what? Constants. So it makes it Fredholm's. It is linear because this has the power 1, this has the power 1. It is non-homogeneous because the free term f of x is not 0. And it is the second kind because the unknown function appears under the integral sign and elsewhere. So second kind. Hope you understand. It's quite simple. Then let's go to the second one. So that one is Volterra's because the b here is replaced with what? X. It is linear because power 1, power 1. Non-homogeneous because this is the free term or the forcing term is non-zero. It is the second kind because our unknown function appears under the integral sign and elsewhere. Then let's take our last example. So it is Volterra because of x here. Non-linear because you could see here it is power 1, but here it is what? Power 2. So it makes it non-linear. It is homogeneous because our free term or forcing term is 0. There is a second kind because you see this and you also see that. Okay, so it's the second kind. So that's it for lesson 2. Don't forget to like the video if it helps you. And thank you. So see you in lesson 3. In lesson 3, we'll talk about how to convert the Volterra's integral equation of the first kind to the second kind using some differentiation techniques. So thank you very much.